All right, this is part one of our relative velocity notes. So, when an object is moving in an already moving medium, its observed velocity relative to the person observing it is not the same as that object's speedometer reading. In other words, the speed that that object perceives itself to be going at. And this situation or this description seems kind of vague. There's a lot of confusing terminology in here that we haven't used consistently. So let me give you a more realistic example. So let's say that you are an observer. You're watching a school bus drive by. And as that school bus is driving by, you're able to see in the windows that one of the bus riders is running from the front of the bus to the back of the bus. What you're going to observe about that rider is going to be different from what that rider is observing of themselves. If the bus is driving east 30 miles per hour and the rider on the bus is running west 3 miles per hour, you're not going to see that rider moving west 3 miles per hour, but you're also not going to observe them moving east 30 miles per hour. You're going to see them moving east, but maybe a little bit slower than 30 miles per hour because their motion of running to the back of the bus is opposing the motion of the bus. In other words, that rider's velocity relative to you is different from the bus's velocity, and it's also different from the rider's velocity. So relative velocity is how fast objects move according to an observer. Now, the way that we're going to find relative velocity, so for example, if I wanted to find out how fast this rider is going to move relative to the observer, relative to me, if I wanted to calculate exactly how fast I'm perceiving them to move, what I'm really going to do is vector addition. I'm going to add the medium's velocity vector to the object's velocity, and I'm just going to draw the resultant vector from adding those two together. So what's important with this is being able to identify the medium's velocity and the object's velocity. So for example, when planes fly, they experience air currents. Sometimes the wind pushes against them, sometimes it pushes them forward. We've got different words that describe the different ways that wind affects the flight of a plane. So let's just do a simple example. A plane is flying at a speed of 100 kilometers per hour. So the pilot of that plane, when they look at their speedometer, it's going to read 100 kilometers per hour. But let's say that that plane at the same time is experiencing something called a tailwind. A tailwind is just wind currents that are in the same direction that you're already moving. In other words, they're propelling you forward, they're pushing you forward. So let's say that this plane is experiencing a tailwind of 25 kilometers per hour. That plane is no longer going to move at perfect 100 kilometers per hour. The wind is going to affect its actual motion. So observers standing below are going to notice that the plane appears to be moving faster than what its speedometer reading is. And that's because it is moving faster. So if the plane's velocity, this is kind of like our object's velocity vector, is a vector that is 100 kilometers per hour in magnitude. And then the wind's vector, this is like the medium that our plane is traveling in. If the medium's vector is 25 kilometers per hour, if I want to figure out what the relative velocity is of this plane, I just need to add these two vectors, my object and my medium, together to get my relative velocity. So if I add the 100 kilometers from the object, from the plane's velocity, with the 25 kilometers from the tailwind, I'm going to get a resultant vector that's 125 kilometers per hour. So relative to the ground, relative to the people who are observing the plane's motion, this plane is actually moving 125 kilometers per hour. So it's going to get to its destination quicker than if it didn't have a tailwind. So let's do a different example. Let's say that instead of a tailwind, let's say this plane was experiencing something called a headwind. Well, a tailwind works in the same direction that the plane is going. It propels it and pushes it forward. A headwind does the opposite. A headwind opposes the plane's motion. It's in the opposite direction. So again, let's say same situation. Let's say our object's velocity, in this case, the plane's velocity vector, is 100 kilometers per hour. And our medium's vector, our wind's vector, is 25 kilometers in the opposite direction because it's a headwind and not a tailwind. My relative velocity is still going to be the sum of these two vectors. The only difference is that instead of them working together, they're going to be in opposition. And I'll show you what I mean by that. If I have 100 kilometers south, let's just say, from my plane's velocity vector, and then I've got the 25 kilometers north from the wind's vector, my resultant is going to be what's left over between those two, which is going to be 75 kilometers per hour south, which is how I end up getting this resultant vector, this relative velocity, right here. So a plane is actually going to get to its destination in a longer amount of time when it's experiencing a headwind. It's going to travel slower than it's intended to. Remember, the speedometer reading that the pilot's going to see is going to read 100 kilometers per hour. But due to the headwind, their actual speed is only going to be 75 kilometers per hour. So relative velocity, while it is relative to the observer, it's also synonymous with being the actual speed that the object is moving at. So let's do one last example. Let's say that the same plane is flying, but instead of a headwind and a tailwind, it experiences a crosswind. Now, crosswind is kind of exactly like it sounds. Instead of being in the same direction as the plane's motion, it's actually across the plane's motion, or it's perpendicular to the plane's motion. So let's say our object's velocity, in this case, the plane's vector, is 100 kilometers. Let's say this is what the speedometer reading says, but the medium it's traveling in, the wind, is 25 kilometers to the west. My relative velocity, again, is still going to be the sum of these two vectors. So I'm still going to combine the 100 kilometer per hour vector from the plane's velocity with the 25 kilometer per hour crosswind from the wind's velocity. And my resultant is going to be exactly what you might expect. My plane's not going to go in the exact direction it intended to. Because the wind is pushing it horizontally, it's going to travel at an angle. So not only is this going to affect the speed, my plane is going to go a little bit faster at 103.1 kilometers per hour, but it's also going to affect the direction of my plane. And this could really be a problem for pilots, because if they're intending to go on a certain route and a crosswind is affecting their direction, it could possibly push them off of their route and into the route of another plane, which could be very potentially dangerous. So pilots have to learn how to calculate their relative velocity and change their object's velocity so that their relative velocity is in the correct direction. And we'll talk about examples where that might be the case later on. But really what we want to be able to do in this lesson is find relative velocity from any situation. So we're going to do one example together of this in part one. So let's say a motorboat is traveling to the east 4 meters per second. I'm going to draw the boat's velocity. 4 meters per second to the east direction. And it's going across a river that has a current of 3 meters per second traveling north. So I'm going to draw the currents vector as 3 meters per second to the north direction. If I wanted to find the resultant velocity, I would just add these two together, and that would be the equivalent of my relative velocity for the motorboat. So let's move these vectors around. I guess I could redraw them to be on the same page as you. If I were to redraw these vectors and add them together, I'm going to draw them tip to tail. So my boat's velocity, I guess I should have drawn that lower, is going to connect to the tail of my current's velocity. And my resultant vector is just going to be from the connection with the very beginning to the very end of this addition. So if I wanted to find the magnitude, I would use Pythagorean theorem to find the magnitude of this vector. So instead of a squared plus b squared equaling c squared, I'm just going to add my components, 4 squared plus 3 squared, and this is going to be equal to the magnitude squared. So I'll end up getting 16 plus 9 equals the magnitude squared to get me 25 equals the magnitude squared. And when I square root, I end up getting 5 meters per second for my magnitude. So this is how fast the boat is going relative to me, the observer. But that's not the only part of the resultant vector I want to know. I also want to know what this direction is, what this theta is. So I'm going to find this theta by using some trig functions. And I've got all of the sides in my triangle here, so I can really use any trig function, but I'm just going to use the most popular one that we use, which is the tangent one, more often than not. So I know that tangent of my angle is equal to the opposite side over the adjacent side. And if I invert this function, now things aren't writing, let's try again, there we go. If I invert this tangent function, I'll be able to solve for theta. So I just need to plug this into my calculator, which I can do here. I'm fairly certain that I can at least. If I do, it was 3 divided by 4 and hit equals. I can hit the second button and do the inverse tangent. That does not seem right. Oh, I guess because I had to hit equals. Yes, all right. I get 36.9 degrees, and that does seem right. So 36.9 degrees is equal to my theta, but remember, when we read the direction of a vector, we don't just give an angle, we're always giving an angle relative to an axis. There's those two different conventions that you use. So you can state the direction of this vector one of two ways and be correct. You could say that this vector is 36.9 degrees away from east. Sometimes that's the easiest convention to use. Or you could say that this is 36.9 degrees north of east. So these are both conventions. We've had a lot of practice using both conventions. So whichever one you're more comfortable with will be fine. So when asked to find the resultant velocity, oops, my highlighter's not working. Let's try. When asked to find the resultant velocity, there's two pieces we're going to need. We're going to need the magnitude of this resultant velocity as well as the direction of this resultant velocity, which could be provided with either of the following conventions. So this is just part 1 of our relative velocity notes. I'm going to end this video and begin part 2 to give you a little bit of a nice chunking there.